The last rule we'll learn is that of the chain rule. The chain rule. This rule tells you how to differentiate a composite function. So the derivative of f of g of x is f prime g of x times g prime of x. Right, f is the outside function, g is the inside function, g is inside of f, and the derivative is the derivative of f with g still being the inside function times the derivative of g. For an example, let's check out a trig function, sine of 8x. So according to the chain rule, when you differentiate to find dy dx, we have 8x inside of sine. So we start from the outside and work our way in. The derivative of sine of 8x is cosine of 8x. That tells you how fast the sine part changes. And then times g prime, the derivative of the inside function, which is 8. So the overall answer is 8 cosine 8x. And the reason I like to use a trig function as a first example is that we know what this 8 does to the graph of sine. For example, usually sine has period 2 pi, which is to say it takes 2 pi radians for sine to complete one wavelength. We know that the new period of sine 8x is 2 pi over 8, which is pi over 4, which makes sense. This 8 is making it go 8 times faster, so the period is 1/8 of the original period. So if I was to sketch that out, that's pi over 2, that's pi over 4, it would look like this. That's one wavelength of sine of 8x. It's going 8 times faster. I'll keep drawing it. This perfect picture that I'm drawing right there. And that's reflected in the chain rule, because how fast the function is changing is how fast sine normally changes, but 8 times faster. So when you multiply by the inside function, that's telling you how many times faster the function is changing. Now for a proof. So we'll prove this with the limit definition. So we know that the derivative of f of g of x is the limit as delta x approaches 0 of, you plug x plus delta x into your function, so f of g of x plus delta x, and then minus f of g of x over delta x, right? It's the change in our composite function over the change in x. For our next step, we're going to introduce a new term, delta g of x. Delta means change, so delta g of x means the change in g of x, which means it's g of x plus delta x minus g of x. Which makes sense. That's how much g changed as x changed from x to x plus delta x. A consequence of this is that if we rearrange these terms a bit, g of x plus delta x is equivalent to g of x plus delta g of x. Right? We just rearrange some terms there, we get this expression right here. That's going to come into play in a few minutes. Now we introduce this into our limit up here. The way we're going to introduce it is we have our limit, the limit as delta x approaches 0, f of g of x plus delta x minus f of g of x over delta x. And we're going to multiply by delta g of x over delta g of x. Right? It doesn't change the value since we multiplied both the numerator and the denominator by it. Then we're going to rearrange our terms. We're going to put that denominator with that numerator, and we're going to put this denominator with that numerator. And actually, when we do two things at one time, we can see here that we have f of g of x plus delta x. And we showed in our previous page that g of x plus delta x is g of x plus delta g of x. So I'm going to substitute this in for that g of x plus delta x to give me f of g of x plus delta g of x, and then minus the f of g of x, all over delta g of x. This delta g of x is that one in the previous statement, and then times delta g of x, which I'll write in its expanded form, over delta x, which came from that one. We're almost there, because remember, we're trying to prove the chain rule, which is that the derivative is f prime g of x times g prime. G prime we already have. This is g prime, right? The limit as delta x goes to 0 of the change in g or the change in x. That is g prime. This is almost f prime g of x. If you notice, this expression looks just like f prime, only instead of x, we have g of x's. Because g of x is the input into f, so it's taken the role of x. The only thing that's off is that we have delta x is going to 0, and this quotient is using g of x as its variable. So we're going to break our limit up into two pieces. Times the limit as delta x goes to 0 of g of x plus delta x minus g of x. Sorry, I got it right tiny again. Bad space management. There we go. And we learned this property in lecture 1 that you can break up a limit as a product. Over here, we're going to go back to the previous page. You can see that as delta x goes to 0, delta g of x just becomes g of x minus g of x, which means as delta x goes to 0, so too does delta g of x, which means I can replace this delta x approaching 0 with delta g of x approaching 0, because this implies that. And now we've got it exactly. This is f prime, where instead of x you have g of x as the input. This is g prime. So now we have f prime g of x times g prime of x.